We all have our faults. Salt Lake City certainly does, as an earthquake-prone area.
We figured, living in Salt Lake City, that we should learn a little bit more about the earthquakes in our region and around the country.
The USGS and UGS have been collecting data on earthquakes for the last 30 years and more, so we scraped the data from the website.
Well, at least we cleaned the CSV after we downloaded it.
We started exploring the data by plotting the locations of the earthquakes across Utah, California, and Oklahoma.
We immediately noticed different groups of earthquake-prone areas throughout each state, so we thought that clustering the earthquakes could help us make sense of all this data.
So we tried some clustering. A lot of clustering. This kind of helped. We'll get back to the clustering later.
We also looked for initial correlations in the dataset to see if certain features could help predict the value of other features. In class, we were told this is called regression.
Initially, it looked like there were some strong correlations. However, these turned out to be latitude and longitude. After all this, regression was unhelpful.
After regression failed, we wanted to find features of this data that could classify the earthquakes by magnitude.
We thought K nearest neighbors was a good place to start, until we computed this confusion matrix.
We then decided to turn to a decision tree-based classification. Here, we were able to achieve high accuracy on both test and training sets of our earthquake data, especially for Utah.
Plus, we were able to draw some fun trees in the process.
Depth of the earthquake turned out to be the most important factor in the classification. This makes sense. The deeper you go into the earth, the stronger the rock and the more energy it can store.
So how good is our ability to detect earthquakes anyway? Are there regions in our state where we need to be doing a better job?
The dataset has an error for each measurement. That is estimated for 3 different axes.
There's horizontal error, which is just the XY displacement on the ground. There's the depth error, which is how far under the ground the earthquake occurred. And then there's the magnitude error, which is the energy that got released by the earthquake.
The horizontal location error, in kilometers, defined as the length of the largest projection of the 3 principal errors on a horizontal plane. The principal errors are the major axes of the error ellipsoid and are mutually perpendicular.
To look at the error in different regions, we used k-means clustering to generate relatively equally sized clusters.
Beautiful clusters. Look at these clusters.
Then we calculated the mean and variance for each error and each cluster.
We looked at the distribution of the variance and the mean, and saw that there were some clear outliers in the horizontal error mean and the horizontal error variance.
So where are these clusters?
2 of them are on the western side of the state. The other one is northeast of the state, but this is Wyoming, so who really cares?
Our analysis suggests that we should commit more resources to measuring earthquakes in these sections of the state, since their data is lower quality than the rest. While this might not be earth-shaking news, we still learned a lot from this project.